learn mathematics.
Alright, we're going to be designing an experiment to look for the annihilation spectra resulting from dark matter collisions in space.
Ooh, dark matter. We better bring a flashlight.
I was making a joke. I'm the boss. I make the jokes.
Well, not that, but essentially for three reasons. Application, calculation, and last and unfortunately least in terms of the time we are given, inspiration. Mathematics is a science of patterns, and we study it to learn how to think logically, critically, and creatively. It can be applied to almost anything and is everywhere you look. In fact, there are specific numbers that we see around ourselves all the time. Together they are called the Fibonacci sequence, and it goes something like this. The third number in the sequence is the first two numbers added together. 0 plus 1 equals 1. The fourth number in the sequence is the second and third numbers added together. 1 plus 1 equals 2. Each successive number is the addition of the previous two numbers in the sequence. Mathematicians in India first described the sequence about 1300 years ago, and an Italian man by the name of Leonardo Pizza, also known as Fibonacci, first introduced it to the West in 1202. He was also responsible for introducing Arabic numerals to Europe, which is the sole reason we're not counting in Roman numerals now. Fibonacci was a mathematician, and in his book Liber Abaci, he described the sequence with a thought experiment about families of infectious bunnies. One boy bunny and a girl bunny together will make a third, and when those three, when they are done, taking turns, will make 5. The easiest ways to find these numbers in nature isn't in bunnies, it's in plants. If you cut a banana into slices, you will see it has 3 distinct sections. An apple has 5. No matter what flower you are looking at, chances are it has 3, 5, 8, 13, or 21 petals.
5 was reportedly used by ancient Greek sculptor Phidias to illustrate the idea of physical perfection. He is said to have used 5 as the ratio between statue's total height and the distance from bottom of its feet to navel, for instance, and also the length of the face divided by its width. There is a whole other patterns in nature that are based on what's called the golden rectangle, a rectangle whose side lengths are successive Fibonacci numbers like 8 and 30. This rectangle can be divided into series of squares whose lengths are also successive Fibonacci numbers, in this case 1 by 1, 2 by 2, 3 by 3, 5 by 5, and 8 by 8. When you draw an arc from one corner of each square to the other, they join to form a spiral that resembles many of the spirals you observe in nature, from unfolding leaves of desert succulent, the arrangement of pinecone lobes, the sunflower seeds, and the curve of waves. Here are some examples of the golden rectangle observed in nature. Seed heads. The head of flower is also subject to Fibonacci processes. Typically, seeds are produced at the center and then migrate towards the outside to fill all the space. Sunflowers provide a great example of spiraling patterns. Pine cones. Similarly, the seed pods on a pine cone are arranged in a spiral pattern. Each cone consists of a pair of spirals, each one spiraling upwards in opposing directions. The number of steps will almost always match a pair of consecutive Fibonacci numbers. For example, a 3 to 5 cone is a cone which meets at the back after 3 steps along the left spiral and 5 steps along the right. Likewise, similar spiraling patterns can be found in pineapples. Shells. The unique property of golden rectangle provides another example. The shape, a rectangle in which the ratio of sides A ratio B is equal to the golden mean, can result in nesting process that can be repeated into infinity, and which takes on the form of a spiral. This is called the logarithmic spiral. Snail shells and nautilus shells follow the logarithmic spiral, and so does the cochlea of the inner ear. It can also
Spiral galaxies also follow the familiar Fibonacci pattern. The Milky Way has several spiral arms, each of them a logarithmic spiral of about 12 degrees. These arms are also prevalent in hurricanes. Faces, both human and non-human, are bound with examples of golden ratio. The mouth and the nose are each positioned at golden sections of the distance between the eyes and the bottom of the chin. Similar proportions can be seen from the side, and even the eye and the ear itself, which follows along a spiral. The most most famous example is probably the Mona Lisa. It's worth noting that every person's body is different, but that averages across populations tend towards phi. It has also been said that the more closely our proportions adhere to phi, the more attractive those traits are perceived. As an example, the most beautiful smiles are those in which the central incisors are 1.618 wider than the lateral incisors, which are 1.618 wider than the canines, and so on. It's quite possible that from an evopsych perspective, that we are primed to like physical forms that adhere to the golden ratio, a potential indicator of reproductive fitness and health. There are much more situations where Fibonacci sequence can be applied in real life. For example, in arrangement of leaves on a stem, the fruitlets of a pineapple. There are thousands of other examples, but these are some of the really well-known ones.